Hello everyone. Today we will be solving an interesting number theory question from last year's Putnam. The problem says let b0 equals 0 and for n greater than or equal to 0, define bn plus 1 as 2bn squared plus bn plus 1, and for each k greater than or equal to 1, show that b sub 2 to the k plus 1 minus 2b sub 2 to the k is divisible by 2 to the 2k plus 2 but not by 2 to the 2k plus 3. So this is equivalent to saying that v2 of b sub 2 to the k plus 1 minus 2 b sub 2 to the k is equal to k plus 2, right? Where v2 denotes the two-adic valuation of n. v2 of n denotes the two-adic valuation of n. Okay, so now we will prove this claim in a few different ways. First, define f of x equal to 2x squared plus x plus 1 and f of x minus y, f of x minus f of y is equal to x minus y times 2x plus 2y plus 1. Okay, so now note that this implies that b sub n plus 1 minus b of n plus 1 is equal to b of n plus m minus b of n times 2b n plus m plus 2bm so this we will label as 1. Okay, equation number 1. This is a very important equation because this side is always odd. So hence, the two-adic valuation of the LHS, the left-hand side, is the same as the two-adic valuation of this. So we will write hence second factor is odd. We have v2 of bn plus n plus 1 minus b of n plus 1 is equal to v2 of bn plus n minus bn. Okay, just so this looks a little less compressed, I will also it down here. Okay, then induction we must have v2 of b of n plus n minus bn is equal to v2 bn. We will call this 2. Okay, now why is this? So I will sketch out the induction very quickly. Just a quick sketch. So the base case is clear. We let n is equal to 0 in this equation, and we get v2 of bm on our right hand side, and then if this equation holds, if 2 holds for any n greater than 0, greater than or equal to 0 for any n actually, then it will hold for bn plus 1 for n plus 1 as well, right? By this relation here. So since the base case is v2 of gives us bn, bn by induction on n, we have v2 of bn plus m minus bn is equal to v2 of bm. Okay, so now we introduce some notation. For brevity, we will write ck as b2 to the k, and aj we will define as 2b m plus j plus 2bj plus 1. Okay, then first we set m equal to 2 to the k. Then we have product from j is equal to 0 to m minus 1 of aj as product from j is equal to 0 to m minus 1 of, well, we use equation 1 again, and we can write this as b m plus j plus 1 minus bj plus 1 by b bm plus j minus bj. Okay, so and now this product telescopes, which is equal to b2m minus bm by bm. Okay, so this is our product, and now this is equal to ck plus 1 minus ck by ck, and we will set this equal to some uk. Okay, now so now we note that the desired evaluation of, I mean, the desired thing we want to show that is divisible by 2 to the 2k plus 2 is c of k plus 1 minus 2ck, which is equal to ck times uk minus 1. So now we will prove so I'm going to call going to call this 3. Okay, and we will prove by induction that V2 of Ck is equal to V2 of lower V2 of Ck is equal to V2 of Uk minus 1, which is equal to K plus 1. The base case is when K is equal to 1, holds. Now this is a step which I will be skipping, the base case, because you will essentially just need to this is our inductions so far, in case I've skipped ahead. So just to be clear, if for some k greater than or equal to 1, v2 of ck is equal to v2 of uk minus 1, it's equal to k plus 1, then we have ck plus 1 is ck times uk plus 1. v2 is uk plus 1, which is equal to 1, because uk is congruent to 1 mod 4, because v2 of uk minus 1 is greater than or equal to, right? So hence v2 of ck plus 1 is equal to v2 of ck plus v2 of uk plus 1 is equal to k plus 1 plus 1 is equal to k plus 2. Now now we have from this the first step of our induction complete. The first step, that v2 of c of k is equal to k plus 1. Now we complete induction by showing v2 uk minus 1, uk plus 1 minus 1 is equal to k plus 2. So first we are going to write uk as product from j is equal to 0 to m minus 1 of aj, and uk plus 1 is equal to product from j is equal to 0 to 2m minus 1 we'll again just let m equal to 2 to the k, m minus 1 of 2 to be b 2m plus j plus bj plus 1. And now we can rewrite this, so this is 2m minus 1. And now we can rewrite this as product from j is equal to 0 to m minus 1. We can reindex the terms so that we pair off the terms such that b of 2m plus j plus 2bj plus 1 times 2b 3m plus j plus bn plus j plus 1. Okay, so this much is clear. So this is uk plus 1. Now we're going to examine each of the individual terms in the product. Firstly, v2 of b2m plus j minus bm plus j is equal to v2 of bm, which is equal to k plus 1 by the inductive hypothesis, right? So bm is equal to ck. Okay, now 2 times bm plus j minus bm plus j is equal to 2b 2m plus j plus 2bj plus 1 minus aj. Hence, we can write 2b 2m j plus 2bj plus 1 as aj plus 2 to the k plus 1, k plus 2 actually, times some alpha j, where alpha j is odd, right? This is because the valuation of this is 2k minus 1, is k plus 1, and we have an extra power of 2 here, so we have k plus 1 plus 1, which is k plus 2, as the exponent of 2 in this, and then we add an aj. So this is some, and then we add a capital aj. Okay, so now this is aj. Now I'm going to define, we're going to also now find v2 of b3m plus j minus bj which is equal to b3m plus j minus m plus j minus 2m plus j minus m plus j plus m plus j, b plus j minus b j. This one does not v2 here, so you can write this like this. So v2 of b3m plus j minus bj is equal to v2 of bm plus j minus bj by 2. Again, we have this as v2 of bm which is equal to k plus 1. And once again, we can rewrite 2b3n plus j plus 2n plus j j plus 1 is equal to aj plus 2 to the k plus 2 times beta j beta j odd. Okay, because you can always just rearrange this. This is roughly by the same logic. Now the product of these two, this is a lot of algebra, product of these two, b2m plus j plus b2j plus 1 times 2b3m plus j plus 2bn plus j plus 1 is equal to aj square plus 2 to the k plus 2 alpha j plus beta j, and since both of them are odd, plus 2 to the k plus 4 alpha j beta j, and we take this mod 2 to the k plus 3, and since this term is even, we get a power of 2 to the k plus 3 here. So taking this mod 2 to the k plus 3, we get aj square, and everything else cancels, so this is just aj square mod 2 to the k plus 3. So now this here is nothing but the term in the product of uk plus 1 here, right? So we can multiply from 0 to m minus 1 of g in 0 to m minus 1 j on both sides, so we get multiplying by j multiplying by j uk that's the product of this that I've just erased, is congruent to, sorry, this is uk plus 1 is congruent to uk the whole square mod 2 to the k plus 3. Hence, v2 of uk plus 1 minus 1, which is what we want, minus uk square minus 1 is equal to v2 of uk plus 1 minus uk square uk square, which is greater than or equal to k plus 3. Okay, but v2 of use k square plus minus 1 is equal to v2 of uk plus 1 plus v2 of uk minus 1 right, and the second term is k plus 1 and the first term is 1, which is, so this is k plus 2. So since v2 of this term must be the same as v2 of uk square minus 1, which is 2 to the k, because k plus 3 is greater than k plus 2. So we have v2 of uk plus 1 minus 1 is equal to k plus 2 as well. Okay, so that completes the induction. So by 3 v2 of ck plus 1 minus 2 ck is equal to v2 of ck plus v2 of uk minus 1, which is equal to 2k plus 2, but ck plus 1 is equal to b sub 2 to the k plus 1. Hence, we have v2 of b sub 2 to the k plus 1 minus b sub 2 to the k, 2 to the k is equal to 2k plus 2. as desired. Okay, so that's the solution. So let's go over it one more time. So first, we wanted to show that the two-adic valuation was 2k plus 2. So we did this by introducing f of x minus f of y, and then noting this key inductive identity, 1. And since the second factor was odd, we got 2 by induction, and we also defined uk as the product of over aj's, and we iterated 1 and used a telescoping product. Then we rewrote ck plus 1 minus 2ck. So then we proved by induction that v2 of ck is equal to v2 of uk minus 1, which is equal to k plus 1. And we let m equal to 2 to the k is equal to 1 wholes. So, and then we did the induction, and we showed that v2 of uk plus 1 minus 1 is equal to k plus 2 if v2 of uk plus 1 minus 1 is equal to 2 to the k, is equal to k plus 1. And then we had some algebra and spade work in between, and then we used some basic valuation tricks to prove that v2 of uk plus 1 minus 1 is equal to k plus 2, which completed the induction. So we used relation number 3, this one, to show that v2 of ck plus 1 minus 2 ck is equal to 2k plus 2, but since ck plus 1 is equal to b sub 2 to the k plus 1, we had the desired valuation. So I think this is a very nice problem. This is a mixture of number theory and dynamics, recursion relations. So a very useful step in some takeaways are in any recursion relation problem, it always helps to define the polynomial, or usually it's a polynomial. In general, the function which the recurrence is satisfying, it often helps to define it, but especially if it's a polynomial and it's integers and so on. When you're working with integers and so on. So it's very useful to define the polynomial and use key facts about the polynomial. In fact, Putnam 2000 A6 was rather similar to this. I would say that was a lot easier, but definitely similar in many ways. So then you use the same trick. And it always helps to induct like the way we did. And another takeaway is that you often have to define a lot of quantities in these kind of problems to actually make any headway towards them. So yeah, I think that's it for this problem. I think it was a very nice problem. It's very challenging. So congratulations to anyone who actually solved it during the contest. And this is a very challenging problem indeed. And yeah. Thank you very much for watching. I hope this video helped.